Have you ever looked up at the night sky and felt a sense of awe? A feeling of connection to something vast, ancient, and profound? The universe is a truly magnificent place. It's filled with 100 billion galaxies, each containing 100 billion stars. But how did it all begin? The story starts not with a bang, but with a stretch. An incredible, unimaginable expansion of space itself. This is cosmic inflation. It was a moment of pure, unadulterated creation. It happened in the very first sliver of a second after the Big Bang, a time so short, it makes the blink of an eye seem like an eternity. In this fleeting instant, the universe grew from something smaller than an atom to something larger than a galaxy. It's a mind-boggling idea, isn't it? That the entire cosmos we see today, all the stars, all the galaxies, all the vast empty spaces between them, was once packed into a point of infinitesimal size. The theory of cosmic inflation suggests that a mysterious energy field, sometimes called the inflaton field, drove this stupendous growth. Think of it like a cosmic spring wound incredibly tight. When it was released, it pushed space apart at a speed that defies all earthly comparison. It was faster than the speed of light. Now you might think nothing can travel faster than light, and you'd be right. Nothing in space can. But this was different. This was space itself expanding. This period of hyper-expansion didn't last long. It was over in less than a trillionth of a second. But its effects were permanent and profound. It smoothed out the universe, making it incredibly uniform on the larger scales. It's why when we look out in any direction, the universe looks roughly the same. Let's journey back to the beginning, to a time before time as we understand it. The universe is just 10 to the minus 36 seconds old. That's a 0 followed by a decimal point, followed by 35 more zeros and then a 1. It is a timescale so short that our human minds can't truly grasp it. At this moment, the universe was a seething cauldron of energy, unimaginably hot and dense. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single superforce. The cosmos was a perfect, symmetrical but unstable place. It was balanced on a knife edge, ready for a dramatic change. This change was triggered by the inflaton field. Imagine a ball resting at the top of a very wide, gently sloping hill. It's in a state of what physicists call a false vacuum. Now this all sounds like a wonderful story, a grand, sweeping narrative of our cosmic origins. But how do we know it's true? Science isn't just about telling stories. It's about testing them against observation and evidence. We can't build a time machine and go back to watch inflation happen. So we must look for its echoes, its fingerprints left on the cosmos. And remarkably, we have found them. The most powerful evidence comes from the oldest light in the universe, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The CMB is astonishingly uniform in temperature, no matter which direction we look. It's about 2.7 Kelvin, or minus 270 degrees Celsius, everywhere. This uniformity was a great mystery. How could regions of the universe that were never in causal contact with each other, that never had time to exchange heat and even out their temperatures, be so alike? Inflation provides a brilliant answer. We live in a universe that is, on the whole, quite stable. The laws of physics appear constant, but the theory of inflation opens up a rather unsettling possibility. The energy field that drove the first inflation, the inflaton, decayed into a lower energy state. But what if the state we are in now is not the true, final rock-bottom energy state? What if our universe is just another false vacuum, a temporary resting place, like that ball on the gentle slope of a hill? What would happen if it received a nudge and started rolling again? What if cosmic inflation started anew? The moment it began, a bubble of this new inflation would appear somewhere in the universe. It could happen right here, in this room, or in a distant galaxy, billions of light years away. Within this bubble, the laws of physics as we know them might cease to exist. The energy of the vacuum would skyrocket, and space would begin to expand at that same unimaginable exponential rate it did at the dawn of time. Let's imagine for a moment the impossible. Let's imagine we could witness this event from a safe distance, which we can't, but let's pretend. If a bubble of new inflation were to appear, say, in the Andromeda Galaxy, we would see nothing change for 2.5 million years. That's how long it would take for the edge of the bubble, traveling at the speed of light, to reach us. The night sky would look exactly the same, the stars would shine, the galaxies would continue their slow cosmic dance. Life on Earth would go on, completely oblivious to the approaching wave of absolute annihilation. There would be no warning. No telescope could detect it. Then one day, it would arrive. For a single, infinitesimal moment, the sky would change. The stars in the direction of the approaching wall would vanish. Then the wall itself would be upon us. It wouldn't be a wall of fire or light, but a wall of transition, a boundary where one set of physical laws ends and another begins. Let's step back from the immediate local effects and consider what would happen on a grander, cosmic scale. If inflation were to restart, not as a bubble of vacuum decay, but as a global change in the nature of space everywhere, the consequences would be just as profound, though perhaps less instantaneous. Imagine that the dark energy that is currently causing the universe's gentle, accelerated expansion suddenly gained the strength of the original inflaton field. The expansion would no longer be gentle. It would become exponential. The universe would start doubling in size every fraction of a second. The first thing we would notice is the disappearance of the night sky. The galaxies outside our own local group, which are already receding from us due to the current expansion, would suddenly rocket away at impossible speeds. Their light would be stretched to infinite wavelengths, red shifting them completely out of view. In a remarkably short time, the sky would become utterly black, devoid of any light save for the stars within our own Milky Way. We would be completely isolated, an island galaxy in an ever-expanding, empty void. The cosmic unraveling would continue to smaller and smaller scales. After galaxies and solar systems have been dismantled, the integrity of individual stars and planets would be the next to be challenged. A star like our Sun is held together by a delicate balance. The inward pull of its own immense gravity is perfectly counteracted by the outward pressure from the nuclear fusion reactions burning in its core. But in a universe undergoing hyperinflation, a new, powerful outward force would be introduced. The very space within the star would be expanding, trying to tear it apart from the inside out. Initially, the star's gravity would be strong enough to resist. But as the expansion became ever more powerful, it would eventually win. Planets like Earth would face a similar brutal end. A planet is held together by its own gravity and the electromagnetic forces that bind its rock and metal. These forces are incredibly strong on a human scale, but they are no match for the power of inflating space-time. Eventually, even individual rocks and mountains would be torn asunder, reduced to a cloud of dust and atoms. This process of destruction would continue right down to the atomic level. The electromagnetic force that holds electrons in orbit around an atomic nucleus would eventually be overwhelmed. Atoms themselves would be ripped apart, their electrons stripped away, leaving a universe filled with a thin gas of free-floating nuclei and electrons. What would all of this mean for life? Life, as we know it, is a product of stability. It requires a steady supply of energy from a star, a stable planetary orbit, and a consistent set of physical and chemical laws. The sudden return of cosmic inflation would shatter all of these requirements. Even in the early stages, as the galaxies began to disappear from view, it would mark a profound philosophical shift for any intelligent beings who witnessed it. The universe would transform from a rich, populated cosmos into a lonely, empty void. The sense of cosmic connection would be replaced by one of ultimate isolation. Ultimately, life is a delicate and complex chemical process. It relies on the precise bonds between atoms to form molecules like DNA and proteins. It relies on the stability of those atoms themselves. When the expansion becomes strong enough to overcome the electromagnetic force, all chemistry ceases. After exploring such a dramatic and terminal fate for our universe, we must ask the crucial question, could this actually happen? Is this a genuine threat we should worry about? Or is it just a fascinating but purely theoretical speculation? The honest answer is that we don't know for sure. Our understanding of the inflaton field, dark energy, and the ultimate nature of the vacuum is still incomplete. According to our best current theories, the vacuum of our universe appears to be remarkably stable. If it is a false vacuum, it is an incredibly long-lived one. The probability of it decaying is thought to be extraordinarily low. Calculations suggest that the lifetime of our current vacuum state is many, many orders of magnitude longer than the current age of the universe. The chance of a bubble of new inflation appearing in our observable universe in any given second is so vanishingly small as to be practically zero. So, you can sleep soundly tonight. While it is a theoretical possibility allowed by physics, it is not considered a plausible near-term threat. It remains a fascinating what-if scenario that pushes our understanding of cosmology to its absolute limits. We live in a special moment, a Goldilocks era of the universe, where the expansion is gentle enough to allow for structure and stars and life. It should fill us with a sense of wonder and a deep appreciation for the stable, beautiful, and life-giving universe we are privileged to inhabit and observe.